Welcome to Digital Electronics Lecture 2. In this lecture, we will discuss about number system. Before starting this subject, this class, we briefly recap what we discussed in lecture 1. In lecture 1, we have discussed about the 4 modules that we are going to study. First module is the number system and logic optimization. Second module is the combinational circuit design. Third module is the sequential circuit design. And fourth module is the analog to digital converter, digital to analog converter, and programmable logic devices. Also, we discuss about the digital system where analog to digital converter basically converts the analog signal and that produce the digital version of the analog signal, and then the digital signal will be processed by the digital electronic circuit and that will be converted back into analog form by digital to analog converter. Also, we understood that how an analog signal can be represented by digits, and that is called a digital signal. And also we understood that what is the digital error or digital conversion error. Now in this class we are going to understand the number systems. Number system is important because the signals are represented by some digit and that digits comes under number system. Conventionally, we have the decimal number system which has the base 10 system. Here we have 0 to 9, total 10 symbols. So if I write this in the form like with the decimal point, before the decimal point the digit D0, D1, D2, D3 like that, and after the decimal point D minus 1, D minus 2, D minus 3 like this. So here the subscript of D represent the position of that particular digit. Now in each position in decimal system we have weightage of 10 to the power 0, 10 to the power 1, 10 to the power 2, 10 to the power 3, and here we have 10 to the power minus 1, 10 to the power minus 2, 10 to the power minus 3 like this. To get the value, we should multiply the digit value with this particular positional weightage. So I will have corresponding decimal value will be D3 into 10 to the power 3 plus D2 into 10 to the power 2 plus D1 into 10 to the power 1 plus D0 into 10 to the power 0 plus D minus 1 into 10 to the power minus 1 plus D minus 2 into 10 to the power minus 2 and so on. Now here D n, where n represents the position that should be within the set 0 to 9. Now, suppose I am taking another number system that has the base 2. Base 2 system has 2 digit or 2 symbols 0 and 1. Base 2 system is used in practical digital circuits because the solid state device has two stable state, either on or off. So on state can be defined by 1, off state can be defined by 0. So in that case, the number, this is called binary system, and this is called the decimal system. Unfortunately, decimal system is not understood by the machine due to these practical constraints. So we have to represent everything in binary form to make the machine understand. So here binary digit is called a bit. Binary digit, that is called a bit, and this bit can be either 0 or 1. Now same thing we can repeat here. The position B0, B1, B2 like this. After decimal point I can have B1, B2, B minus 2, B minus 3 like this. Now each position having a weightage of 2 to the power 0 because it is a base 2 system. So the weightage will be the base to the power 0, base to the power 1, that is 2 to the power 1, 2 to the power 2, here 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3 like this. And when we are calculating its decimal equivalent, each bit value should be multiplied by its weightage. Let us take an example to find its decimal equivalent. Suppose I have a number 1010.11, and this is a base 2 system that is represented by subscript 2. Now I want to convert into its decimal form. So before the decimal point I have a weightage of 2 to the power 0, 2 to the power 1, 2 to the power 2 and 2 to the power 3. After decimal point I have 2 to the power minus 1, then 2 to the power minus 2. So its decimal equivalent will be 1 into 2 to the power 3 plus 0 into 2 to the power 2 plus 1 into 2 to the power 1 plus 0 into 2 to the power 0 plus 1 into 2 to the power minus 1 plus 1 into 2 to the power minus 2. That will give you 8 plus 0 plus 2 plus 0 plus 0.5 plus 0.25. Then if we add it, it will become 10.75. So this is the decimal equivalent of this binary number. In the same way, I can have base 8 system where I have symbol 0 to 7. Total 8 symbols are there. In the base 8 system, if we have a number 23.2, to convert into decimal, before the decimal point the weightage is 8 to the power 0, then 8 to the power 1, and after the decimal point we have a weightage of 8 to the power minus 1. So as per rule, we will multiply 2 with 8 to the power 1 plus 3 into 8 to the power 0 plus 2 into 8 to the power minus 1. That will generate the output 16 plus 3 plus 0.25. So that will be 19.25. So the octal number (23.2) is converted into decimal, and the decimal equivalent is 19.25. So the octal number system, so base 8 system is called octal system. Here we have total 8 symbols. In the same way, we have the hexadecimal system that will be discussed in the next class. Thank you.